We are still in Chapter 7, the very big, the very long Chapter 7. We're stacking concepts on top of each other, learning new concepts every single class, and they're building on top of each other. Last class we learned about Lewis dot structures. We learned that we can add one dot to each of the four sides, and these dots represent the valence electrons. Each dot is one electron VE. I'm using VE because we will see that on potentially a worksheet. The old worksheet, the one that I'm used to giving, is VE on it. So that's why I'm used to writing VE. So those are our valence electrons. And remember that the number of valence electrons that we have for an element, for a main group element, is based on the number of the group that it's in with that A designation for the group. Let's get out our blindingly bright green laser pointer to make it hard to see what I'm pointing at. So for example, our 1A, 2A columns, those are our alkali and alkaline earth metals. Skipping over to the boron group, 3A, carbon 4A, nitrogen 5A, oxygen 6A, fluorine 7A, helium 8A. Each of those columns has that number of valence electrons. That was our shortcut that we learned last time. We also talked about where we got that from as our electron configurations. And that's how we figure out how many dots that we have. We can also represent bonds, either the sharing or transfer of electrons in bonding. Ionic bonds involve a transfer of electrons. These are like in ionic compounds. What's in an ionic compound? What are the two parts? Typically metal and a nonmetal cation, anion. Positively charged, negatively charged ions. Ions are in ionic bonds. And in covalent bonds, the electrons are shared, and those are molecular compounds. And molecular compounds are going to be nonmetals only, and maybe also hydrogen will be in there. And we've got our octet rule. The oct prefix here, remember, counting for 8, standing for 8. The octet rule says that we are transferring or sharing electrons to get outer shells with 8 electrons. Either adding extra electrons in, like if we're fluorine, we need to add 1 electron, either by sharing it, bond, or stealing it. It would have the same number of electrons as neon. Alternatively, with our metals like sodium, sodium has 1 valence electron in its outer shell. If we take that, or if it loses that, then it wraps back around on the periodic table. It would also be like neon. It would have 10 valence electrons because we pulled off the entire outer shell. Let's write Lewis structures for aluminum and selenium. What is our symbol for aluminum? Al. So we find Al on the periodic table. It's right under boron. So aluminum is going to have 3 valence electrons. We'll put in 3 dots. Dot, dot, dot. What's the symbol for selenium? Se. Capital S, lowercase e. We find selenium on the periodic table. It's below sulfur. So it's going to have how many valence electrons? 6. 1, 2, 3, 4, and then double up 5 and 6. That's it. That's all we do with it. We will be doing more, but some review. So when metals bond with nonmetals, like aluminum bonding with selenium, electrons are transferred. Moved from the metal to the nonmetal. Metals lose electrons, nonmetals gain electrons. And when those electrons are transferred, the metal becomes a cation. So this would be, for example, Al3+, and the nonmetal becomes an anion, like Se2-. That's negatively charged, and what do they say in dating? Opposites attract. The aluminum and the selenium will be attracted to each other because they're opposites. Magnetic forces bring them together. And that attraction results in the ionic compound. And they'll self-assemble if you had them in solution. They might self-assemble and form the compound. In Lewis theory, we represent the transfer of electrons by moving the electron dots from the metal to the nonmetal. So we are transferring dots instead of transferring electrons. Let's write Lewis structures for potassium and chlorine and show the electron transfer bond. So potassium is K. Potassium has 1 valence electron. Chlorine has the symbol Cl. It has 7 valence electrons. So we put in 4 dots, 1 on each of never eat soggy waffles, and then we can double them up after that. You can double them up on any side. I know what we're doing next, so I doubled them up in a specific way. I'm going to actually change the color of our potassium's dot. When these two things go to bond, who's giving what? Potassium is donating the electron, or you can think of it as chlorine is stealing the electron. So now we've got potassium with a positive charge, and we've got chlorine with 1 more electron, and this would have a negative charge. So chlorine has 2, 4, 6, 8 electrons, which is a full what? Does anyone know? Octet. And potassium also secretly has a full octet. But Mr. K, there's no electrons there. 0 is not equal to 8. That's true. If we look at where potassium is on the periodic table, though, right, it's an alkali metal. If we take 1 electron off, how many electrons does it have? It normally has 19. If we take 1 off of that, how many does it have? 18. 18 electrons is argon. If we did an electron configuration for potassium, we'll do a shortened one. I'm going to start us with neon. Then it would be 3s2, 3p6, and then the valence electron that it has, the 4s1. So that's this blue electron is this 4s1. This got transferred to the chlorine. And so now, down below, the potassium ion has this electron configuration. We've revealed the inner octet. We've opened the inner, anyway. The 3 is now our highest n number, and it's got 2 plus 6 for 8, which is full octet. So that's why that works. So the chloride ion has an octet. Potassium lost its only valence electron and is left with an octet in the previous shell, which is now the valence shell. Previous shell being n equals 3. And the Lewis structure of an anion is usually written within brackets with the charge in the upper right corner, like I did with the chlorine. I'll draw that in real quick again for us. Why do we have the brackets? other than because. Why does your house have fences, assuming you live in a property? Why does the area you live typically have fences in California? So that you know the area of land that you're supposed to live on. Anything that's in the fences is supposed to be yours. Anything that's outside of the fences is probably somebody else's. This is the same thing. This is fences for Lewis structures. So the fences are saying that this whole thing inside of the brackets overall has a 1 negative charge. Just the whole thing inside of there. This will also make more sense when we get to polyatomic ions, because we're also going to use brackets to encompass a larger area, and we're going to say this whole area has a 1 negative, 2 negative, 3 negative charge. So that's sort of what we're doing here. This also makes it clear that these electrons on the left side do not belong to potassium. Potassium, 0 dots. Chlorine, 8 dots. So it's just keep them separated. If we don't do the brackets, then it looks like something else, and we'll see what that something else is in a bit. Write the Lewis structure of the compound neighbor. So doing the Lewis structure of the compound sodium bromide, Na and Br are the two elements that we have. Sodium has 1 valence electron. Bromine is a halogen, so it's going to have 7 valence electrons. Sodium is a metal. Bromine is a nonmetal. And so when they get together, bromine says, hey, I'm going to take that electron from you right now. And sodium says, okay. And so that electron transfers. We now have the bromide ion. That electron is off limits to sodium. We put it in brackets. We give it the negative charge in the top right corner. Sodium lost 1 electron, so it gets a 1 positive charge. And that would be our Lewis structure. We can also do this with things that are not alkali metals and halogens, which our last two things were. We can also show an electron transfer to form calcium chloride. So we're going to start with calcium atoms and chlorine atoms. Calcium is an alkaline earth metal, meaning that it's got 2 valence electrons. Chlorine is still a halogen, so it has 7 valence electrons. Got a little ahead of myself. What's going to happen when calcium meets chlorine in a dark alley? Yeah. Pow, bam, biff, zap, zow. Calcium's getting mugged for its atom, or for its electron. Chlorine says, that's a lovely electron you've got there. It'd be a shame if something happened to it. And so this is going to turn into something that looks like this. And chlorine is now protective of that electron that it picked up. Is chlorine happy? Chlorine is very happy. Chlorine loves taking an electron. Chlorine has a full octet. That's why we say that it's happy. Full octet equals happy. It probably comes as no surprise to you that atoms don't actually feel emotions. So happy just means it's got a full octet. It's not going to do anything else, probably. Is calcium happy? Calcium is not happy. Calcium has 1 electron, and calcium would rather have no valence electrons, because that would unlock the inner octet, the power within. How can calcium get rid of its one valence electron that it has now? Fighting sounds. There's another chlorine waiting in the very next alley. Believe it or not, calcium's having a great night. So this other chlorine comes along and says, hey, that's a nice electron you've got there. It'd be a shame if something happened to it. Why don't I hold on to it for you? And we have to shrink that down because I wrote too big. So this other calcium comes along. It steals that other valence electron. Calcium has now an empty octet, which is a full octet because the inner octet has been revealed. And the other chlorine and the original chlorine both have their full octets, so everyone's actually happy here. Everything is nice and happy and satisfied. Any questions about the process there? So if you need to, when we're doing ionic compounds, you can always invoke another of whatever things we're dealing with. Typically, if there's one around, there's two around. If there's two around, there's probably three around. If there's three around, there's probably four around for whatever we're dealing with. Oh, also the thing that we get out of this is this predicts, since chlorines are both happy and calcium's happy, this also predicts what our ionic compound formula would be. And I need to write a number 3 so we know what the order is. We've got calcium. How many calciums do we have? Just one. How many chlorines do we have? 2. So CaCl2 is what Lewis theory predicts our compound's formula would be, which we could have also gotten because we know that calcium's a 2+, we know that chlorine's a 1-. We could have swapped and dropped, and we would have gotten the same thing. We're typically not going to be using Lewis theory to come up with ionic compound structures because it takes a while compared to just 2+, 1-, do the math, CaCl2. We can do the same idea with magnesium and nitrogen. Magnesium has what symbol? Mg. How many dots are we drawing on Mg? We are drawing 2. It's in the second group. It's an alkaline earth metal. It's got 2 valence electrons, 2 dots. And nitrogen has the symbol N. Nitrogen has how many valence electrons? 5. It's in the 5a column, or the nitrogen group, or the pnictogens, which has a P in the front. That's our fun fact. So 5 dots. What's going to happen when magnesium and nitrogen meet? Nitrogen is going to take magnesium's 2 electrons. Switching the color to blue. So we transfer those over. And this gives us this. It's now magnesium 2+. And nitrogen, happy, unhappy? Unhappy. Magnesium, happy, unhappy? Magnesium, happy. We took off the outer shell. We're going to say happy. We're going to say not happy. What would make nitrogen happy? One more electron. Where could we get another electron from? Yep, we can get it from another magnesium. Where there's 1, there's probably 2. So another magnesium comes along. How many electrons does this magnesium have? This one also has 2. So nitrogen is going to steal one of those. If you don't want to write along with all this, that's totally cool. I'm going to start doing shortcuts pretty soon here. So we steal one of those, and now nitrogen has picked up how many electrons? How many bonus electrons does nitrogen have? 3. So it's going to have a 3 negative charge. Is nitrogen happy now? Nitrogen is happy. What about magnesium, number 2? Happy, unhappy? Unhappy. What would it like to do? It wants to give away its 1 electron, and it can give that 1 electron away to another nitrogen. So a second nitrogen has entered the Lewis structure. This one also has 5 valence electrons. We transfer that electron. And this is where I start taking shortcuts. The magnesium now has a 2+, and it's happy. Nitrogen, unhappy. Why is it unhappy? It doesn't have a full octet. It needs 2 more electrons. Where can it get those 2 electrons from? Another magnesium. So we say, well, if there's 2, there's probably 3. There's another magnesium. It also has 2 valence electrons. And this magnesium would love nothing more than to just give away those 2 electrons to form a nice, stable, solid ionic compound. And that would look like this. And now the nitrogen is happy. The third magnesium is also happy. Whole lot of work to come up with Mg. We've got 3 of them. And N, nitrogen, we've got 2 of them. So this is the formula that we're predicting for magnesium and nitrogen based on our Lewis dot structure and giving away electrons. Of course, it would have been much faster. We know that it's a magnesium 2+ when it forms an ion. We know that it's a nitrogen 3- when it forms the nitrite ion. We do our little swap and drop, and we would have Mg3 N2. Much faster than doing the Lewis structure. So we're not really doing this for the sake of ionic compounds. We also should be able to show ionic compounds. I usually put some of those on the exam. So we should still be able to show stuff like this. I'm not going to give you something that's like this, many things. If anything, it's going to be 2-to-1, 1-to-1, something like that. Otherwise, it takes up too much space. The real reason that we're doing Lewis structures is for covalent Lewis structures. So when nonmetals bond with other nonmetals, a molecular compound is formed. And molecular compounds share their electrons. And because they're sharing their electrons, they're not taking on positive and negative charges, which means that we can't predict what their formula is going to be or how many bonds they're going to have just based on charges. We can't swap and drop our way into molecular compounds. This is where Lewis theory helps us out. So in Lewis theory, covalent bonding, sharing, electron bonding is represented by our next door neighbor atoms sharing their valence electrons with the goal of attaining octets. And shared electrons count toward both octets. counts for both of them. Consider the Lewis structures for hydrogen and oxygen. Okay. I'm considering. Hydrogen has 1 electron. Oxygen has 6. In water, H2O, hydrogen and oxygen share their electrons. So we would have another hydrogen in here as well. This oxygen in the middle has 6 electrons. It wants 2 more electrons. It could steal them, but hydrogen is also a nonmetal, and so it's not going to be able to just steal them. It's going to have to share them. So we can share up some of these electrons. And one of the ways that we can draw this, I'm going to retcon our hydrogen's electrons to be blue so that we can see the difference. We've got hydrogen, oxygen, hydrogen. And if we just draw them real close to each other, now they're sharing. This is one of the ways that we can represent bonding. So these 2 electrons are shared. These 2 electrons are shared. So these 2 electrons count towards hydrogen's duet. Hydrogen being in the row 1 only has access to 1 S, whatever the symbol for S is. 1s, so it can only get 2 electrons with just 2. If it's duet, hydrogen's happy. Same for the other hydrogen because it's also a hydrogen. The oxygen in the middle, though, wants a full octet, and now it's got 8 electrons around it. Notice that we don't have any brackets, we don't have any landlines, we don't have any fences. That means that they're sharing. So this is what I was talking about earlier. This is one of the reasons that we have brackets for ionic compounds to show that we're sharing or not. So hydrogen has its duet, oxygen has octet. And so everyone's happy. Do we have any questions so far about where do we get those number of electrons? Why are we drawing dots? Is this chemistry class? All right, cool. It is chemistry class, by the way. So with covalent Lewis structures, this is where our electrons are shared. We've got different types of pairs, pairs being 2 electrons. We have bonding pairs. These are the ones that are shared. Bonding pairs or bonds. And we also have lone pairs or non-bonding electrons. These are only on 1 atom. They're on only 1 atom. Let's look at our structure from before for water. We had said that these ones between, these pairs between, are shared because they're between 2 symbols. So if you're between 2 symbols, that means that they are sharing. So between 2 atoms means they are shared, they're bonding. Just like the memories that you make with your friends in chemistry class, bring you closer together, bonding. So those are our shared pairs. And we also have these other two, and these other two are lone pairs. These are only on the oxygen. They're not shared with hydrogen. Typically, we are not going to use dots if we have bonds. So these shared electrons, it can get confusing when we've got all of these dots, and so we use a different notation most of the time. And that's showing the bonding pairs of the shared electrons as lines. And so this that we've got here, love that I have to delete so much stuff now. Just complaining about nothing. That, right, that's one way that we can represent it. Or we can upgrade it. H, one line, O, with its two lone pairs, and a line for the other hydrogen. So you can sort of think of this, we took the lone pairs, we rotated them 90 degrees, and then we connected the dots. So if we draw it in like little barbells, it might look something like that. Each line represents how many electrons? 2 electrons. One line, 2 electrons. And this is what we are going to be using going forward. We're not going to be using the dots in between because everyone else uses the lines. This is pretty much universally everyone uses lines. You will still see sometimes people using the dots, but I think that's a lot less common. Why put 2 dots when you could put 1 line? Lewis' theory also explains why our halogens form diatomic molecules. Hopefully you remember that horses need oats for clear brown eyes, or Brinkelhofer H7, one of our mnemonics, any of our mnemonics for diatomic elements. Fluorine, chlorine, bromine, iodine are halogens, and they form diatomic molecules. So when they are hanging out, if they're just out and about, they're going to pair up. They're never going alone. So for bromine, it's going to have how many valence electrons? 7. And if there's another one around, which there probably is, if there's one, there's probably 2. It's also going to have 7. Now, if bromine gets in a fight with another bromine, there's no winner, right? They're the same thing. So we can't steal electrons, but we can use the power of friendship. We can share those electrons. And so what this turns into is swap out that for 1 line. And now let's count up our valence electrons. Bromine on the left, we've got 2, 4, 6 from lone pairs. Plus 2 because of our bond. Which gives us a total of 8 electrons, which is a full octet. And it's the same for the other bromine because it's the same thing. 2, 4, 6 valence electrons in the form of lone pairs, plus another 2 in our bond to give us a full octet. So Br2 gets full octets for both bromines. They're stable, they're happy. It's going to be the same for iodine, for chlorine, for fluorine, our other halogens, because they're all sharing 1 electron. This also predicts why hydrogen exists as diatomic molecules. hydrogens have one valence electron. They're also the same power level. They can't beat each other up and steal the electrons. And so instead, they share. So hydrogen with one bond to another hydrogen. There's 2 electrons in the bond because there's one line. Hydrogen has its duet smiley face. It's happy. We can also have double and triple bonds. So for example, oxygen, which also exists as a diatomic molecule. We've got 2 oxygens. Our oxygens each have 6 valence electrons. They have 6, more. And so what they can do is they can share 2 electrons. When they share the electrons, they count both octets. So the oxygen on the left essentially gained 2 electrons. The oxygen on the right is essentially gained 2 electrons. So we've got our oxygens. They're sharing 2 pairs of electrons. We draw 2 lines, or an equal sign. And we still have our 2 lone pairs. So we've got 4 electrons from lone pairs, 2 on top, 2 on bottom. And we also have 2 lines times 2 electrons, 4 electrons from bonds. 4 plus 4 is 8. Eight electrons, full octet, smiley face. Do we have any confusions so far? We are still building, by the way. We're on slide 95, and there's like 150 slides. We've got at least 2 more concepts we're going to be adding on top of this. So please make sure that you're keeping up. If you're confused, you need to ask for help. You need to figure it out on your own. You need to go see Logan. You need to go to the tutoring center. Whatever you need to do to make sure that you're keeping caught up on the material, that you're not falling behind, because we're going to keep stacking ideas. And if you try to build a Jenga tower and you're missing the bottom blocks, you're not going to be building a Jenga tower, you're going to be picking up blocks. And that's what we're doing. Okay, so each oxygen atom has an octet because the additional bonding pair, the second bond, counts towards the octet of both oxygen atoms. Each of these lines represents 2 electrons, 2 times 2, 4 electrons in the bonds, and they're happy. So we've got a double bond, 2 electron pairs, pairs of course being 2 electrons. These are shared just between 2 atoms. Double bonds, as you might expect, are shorter and stronger than single bonds. Bonds are kind of like rubber bands. And the nuclei of the atoms are both positively charged, so you've got little magnets repelling each other, but you put a rubber band on them, and that's going to keep them sort of together. We're assuming a lot of things here. If you put on another rubber band and you have the strength of 2 rubber bands, that's going to pull them a little bit closer because the rubber band is pulling them in. They're still repelling each other, so they're not touching. And since we've got two of them, they're going to be stronger. Double bonds are stronger than single bonds. The internuclear distance is a little bit shorter. It's 121 picometers versus 148 picometers. All that we're saying there, you don't have to know those numbers. Forget them. Forget you ever saw them. This just means they're closer together. They're shorter bonds. They're stronger bonds. Consider N2. How many electrons does nitrogen have in its valence shell? 5. Why did we get 5? Because of the column that it's in, right? It's in 5A. So 5 valence electrons. So 5 dots would look like that. If they have 5 dots, how many more dots do they need to be happy? We need 3 more to be happy. Three more to be octet. So share a bond. Now we've got a bond. How many electrons does each nitrogen have now? 6. Which is not an octet. I'm going to slide all this over. Yoicks. Next frame. What if we do, as DJ Khaled says, another one? This would look like this. We've now got double bond technology unlocked. Is it enough? It's not enough. We've got 4 electrons in the bond, another 2, that's 6, plus 1 more, 7. We need 1 more electron. We can also tell because we've got lone pair, or lone electron. Lone electron, usually bad. And so we can do it one more time. And that would look like this. Now we've got you. That's what it's called. Don't get mad at me for it. Now they've got 8 electrons each, which is octet. Lines, 3 bonds, 3 bonds, 2 electrons each, 6 electrons, plus lone pairs. 1 lone pair each. Two electrons plus 6 electrons. 8 electrons. They're happy. So each nitrogen atom with 3 pairs of electrons are shared. So now we're triple bonding, we're not just double bonding. Triple bonds. Triple bonds, each bond is 1. Triple meaning we've got 3 bonds. Again, shared just between 2 atoms. They're shorter and stronger than double bonds. For nitrogen, the triple bond is 110 picometers. A double bond would be 124. 110 is smaller than 124. All we're saying is they're shorter. And nitrogen, which makes up 78% or so of our air, because it has a very strong, very short triple bond, makes it relatively unreactive. Triple bonds are very stable because they're very strong. You can sort of think of bonds as like 3 like movie scene action figure dude reaching off of a cliff arms. If you just have one of them, the hero might be able to pull their hand up off the cliff. If you've got somehow three of them, if one of those breaks, they still have two other and they can reestablish that third one. That's the same way that bonds work. So it's sort of like if you break one, it's going to try to reform. You have to kind of break all three at the same time, and that's going to take a lot of energy. Have we heard of nitro beverages? Probably nitro cold brew, or maybe if any of us are above 21 or have access to alcohol. Guinness, right? Guinness famously has nitrogen in it. This is just a fun fact that I'm sharing with you. So nitro, when we're talking about drinks, means nitrogen gas instead of carbon dioxide or carbonated. So it's actually a different gas that's in your, if you get a nitro cold brew, either in a can or fresh from somewhere. If it's fresh, they're adding nitrogen gas in after they make it. They've got a cylinder or a tank or a jug of nitrogen that they're adding in to make it that way. Usually sodas and other things have carbon dioxide in them. Nitrogen gives you a slightly different bubble profile. They're usually smaller, so people often say that Guinness is exceptionally smooth. That's largely due to its nitrogen that it's got in there. Other drinks that have nitrogen, you can probably also taste and feel the difference between a nitro-infused versus a carbon dioxide-infused beverage. Okay. Rules. So we've learned the basics. We've got lone pairs. Lone pairs are where the electrons are just on one atom. We can also have different amounts of bonds. 1, 2, or 3 bonds. 4 bonds is also possible. We're not going to see it in this class. So 3 bonds is the maximum for us. And each of these bonds is 2 electrons. We also know that we can figure out the number of electrons that we put around our initial thing based on the column that it's in. For example, nitrogen being in 5A means that it's going to have 5 valence electrons. Remember that this numbering system is just for our main group, so we skip over our entire transition metals. You can also just take the 1 off the front when you're in the P block, the boron, carbon, nitrogen, oxygen, fluorine, helium, those groups. So oxygen is in 16, take the 1 off the front. That's the wrong tool. Oxygen in 16, take off the 1 on the front, add an A at the end, now it's 6A. It's the other way we can come up with that. So oxygen would have 6 valence electrons. Now we're going to learn rules for putting them together, making covalent compounds. First step, we're going to do our best to write the correct skeletal structure. What's a skeleton? Bones. With things on them? No, bare bones. So our correct skeletal structure is bare bones for the molecule, just what it looks like, just the atoms. So we're showing the relative positions of the atoms. One of our rules, hydrogen atoms are always terminal atoms. They're at the end. Terminal here meaning at the end. The reason that hydrogen is always terminal is that hydrogen only forms 1 bond. Ever. Mostly. Probably always 1, except sometimes when it's 2. But for us, 1. Only 1. Hydrogen can only form 1 bond. If you can only bond to one thing, then it has to be at the end, regardless of where you put it. Many of our molecules will tend to be symmetrical. What does symmetrical mean? The same on both sides. So the left side, the right side should look like mirrored images. or the top and the bottom should look like mirrored images. Molecules tend to be symmetrical because there's stability in symmetry. So when a molecule contains several atoms of the same type, they will tend to be in mirrored positions, oftentimes terminal positions. There's lots and lots of exceptions. It sort of is just like a we're going to have to experience it, we're going to have to practice it to figure out how it works. Sometimes I'll just give it to us. So starting out, we just want where are the atoms? Put their symbols in, try to make them look nice, try to make it symmetrical. Then we're going to calculate the total number of electrons. We're going to add up the valence electrons of each atom that's in our molecule. If we have ions, we're going to add 1 electron for negative charges, subtract 1 electron for positive charges. So like, for example, PO4 3-. This 3- means add 3 electrons. So we're going to need 3 extra electrons when we're coming up with the Lewis structure for something like PO4 3-. For any of our main group elements, which is most of them that we're going to deal with, it's just the group number, the thing that I was pointing out on this side. And then we're going to distribute our electrons. We're going to start with placing bonds. It's a molecule, so we need to place bonds so that everything's connected. This doesn't mean that all of the atoms are connected to all of the other atoms. It just means that they're all connected to at least one other thing with one line. I don't know why I drew that letter. Avoid circles. So for example, if we've got 3 things and we have to get them all connected, what we're going to do is we would connect them this way. We are not going to connect them a 3rd time. That would be a triangle. That would be a circle of 3 things. That's going to explode. I mean that in the literal sense. If you made that, it would probably explode. You look at it sideways, it's going to explode. So we can't do a red X. We would not be doing that. It would just be connecting these 2 things together. That way it's actually a molecule. And then we'll distribute our remaining electrons. Whatever is left after we've placed our bonds, we're going to start from the outside in. And our goal is completing as many octets as we can, starting from the outside, working our way towards the inside. A lot of the time, we will not end up with full octets doing this. So there's another step. More steps. Got to get our steps in. Any of our atoms then at that point lacks an octet, we can double or triple bond to give them octets. And we can do this by moving lone pairs from terminal atoms. To form double / triple bonds. We'll do this as many times as is necessary. We will do some examples, so if you're confused about just like the steps in abstract, that's okay. We're going to go through, I'll talk through the steps. Lewis structure for H2O. We've got 2 hydrogens, we've got 1 oxygen. We need to lay out the skeleton. So we need to place 2 hydrogens, we need to place 1 oxygen. What do hydrogen atoms always have to be? Terminal. They have to be at the end. Our other thing is oxygen. Oxygen is the only thing that's not a hydrogen that we have here, so it has to go in the middle. This is also nice because it's symmetrical. If we draw a little line here, the left side looks the same as the right side. They're mirrored. So symmetry, we've got that. Good. And then we want to count up how many valence electrons. We've got 2 hydrogens. Hydrogens, we've got 2 of them. How many valence electrons does each hydrogen have? How many electrons does each hydrogen have? How many dots would we give it? 1. So that's a total of 2 valence electrons from our hydrogens. We also have an oxygen. We've got 1 of them. How many dots does an oxygen get? It's going to get 6. 1 times 6, easy math. That's 6. So we've got 8 valence electrons, 8 dots that we get to play with. Step 3, we want to place our bonds. And after that, lone pairs. To get everything connected, we need a line connecting all the things. So we're going to add in a line between hydrogen and oxygen and hydrogen. So we've got 2 lines to get everything connected. How many electrons are in 2 lines? How many total electrons? 4. Each line is how many electrons? 2. Each bond is 2 electrons. So we're subtracting 4 bonding electrons. Be is bonding electrons. Which means that we've got how many remaining? We've got 4 remaining electrons, and we have to add these in as dots or as lone pairs. Where do we want to start when we're adding in lone pairs? Inside, outside, upside, downside? Outside, work our way inside. Can we add any more dots to our hydrogens? No, we can't. Hydrogen's got its duet, it's got its 1 bond, it's done. So that means that we get to add them onto the oxygen. We've got 4 remaining electrons. We place in 4 dots. And now we have no electrons left. Now we have to check, do we have octets? Or in the case of our hydrogens, do we have duets? Our hydrogens have their 1 bond. 1 bond is how many electrons? It's 2 electrons. Each hydrogen has its 2 electrons. Hydrogen has duets. Hydrogen has its duet. It's happy. Oxygen, does it have a full octet? Think. Computing, processing. What do we think? Yes, it does have its full octet. We have 2 electrons in the left bond, 2 electrons in the right bond, 4 electrons from bonds. We've got 2 electrons in the top lone pair, 2 electrons in the bottom lone pair, 4 electrons from lone pairs. So oxygen has octet. So it is happy, it's content. Everyone has what it wants. So this would be a good Lewis structure for H2O. Do you have questions about why I did any of those steps, where I got some of those numbers from? Any deeply intrusive personal questions? All right, great. We love to see it. Let's write a Lewis structure for H2CO. We need to do the skeletal structure first. It would be normal for you to think that we do something like this. This has one line of symmetry through it. There's a secret second option that's actually better. We move one of these, and we put it on top, or we could also put it on the bottom, but I'm going to do it putting it up on the top. So if we move the oxygen up and we move the hydrogen over, now we also have a vertical plane of symmetry. This is more symmetrical, so this would be the better option. Also, I know in my head from lots of chemistry experience that this is how it's supposed to look. So that's our skeletal structure. Then we need to get our valence electrons. We've got hydrogen, we've got 2 of them. How many dots does each hydrogen get? How many does it bring in? 1. So 2 valence electrons from our hydrogens total. We've got a carbon, we've got 1 of them. How many dots would carbon have? It would bring in 4 valence electrons. And what about oxygen? It's going to be 6. So 2 plus 4 plus 6 is 12 valence electrons. Step 3, we're doing our bonds and lone pairs. We need to get everything connected. Go ahead and think to yourself or work by yourself to figure out the best way to connect these so that everything's all hooked up. All right, big reveal. We are going to be connecting our hydrogen to our carbon. I'm assuming that we probably all got that. We're also going to be connecting our oxygen to our carbon. I'm hopeful that we also got that one. Do we need more lines to connect everything? We don't need more lines. We've got everything connected. It's all hooked up in one unit. We would not be able to do these fourth and fifth lines. Why? It's triangles. Triangles love to explode in chemistry. Also, hydrogen can only have 1 bond, so we can't do this for that reason also. So we're not going to add those in. We're done here. How many lines did we draw in? 3 lines. How many electrons are in each line? 2. 2 times 3? 6. Two electrons per bond times 3 bonds. We used up 6 electrons just bonding, which means that we've got 6 remaining electrons. Where can we place our 6 electrons? Hydrogens already have their duets, so our hydrogens are happy. We'll give them little smiley faces so we know we're done with them. We start from the outside in. Oxygen is our only other atom. It currently has how many electrons? 2. It has 2 electrons because of the bonds, so it can take how many more? Can take 6 more, very convenient. So we can place all 6 of our electrons on the oxygen. So now we've got no electrons left.
Did we ever put on the carbon on top?
We would start, you should always start with putting them on oxygen until you're further in your chemistry journey, and then you just might know where they go. But for now, this system is what we're working with. And then step 4, check octets and fill anything out that we need to. We already talked about our oxygen. It's got its octet. The one that we haven't checked yet is our carbon. How many electrons does carbon have that counts towards its octet? It has 3 bonds. 3 bonds times 2 electrons, 6 electrons. So carbon only has 6 electrons, which is not an octet. Carbon is not happy. How can we get more electrons to carbon if we don't have any more electrons to place?
We can add another bond to carbon and oxygen.
We can add another bond. We can share. So we can take one of these and put it in to make it a double bond. And what that turns into is this and that. And because these electrons are still in the bond, oxygen still has access to them. It's got 2 lines, 2, 4 electrons, 6 electrons, 8 electrons. Oxygen is happy. We didn't change anything about our hydrogens, so they're happy. Carbon in the middle now has 4 bonds with 2 electrons each. 4 times 2 gives us 8. So carbon is also happy. Full octets, all electrons placed. We're done. We will talk about polyatomic ions next week.